Morning class you can ask. Anything not clear in the morning talk? Yes. No, Faraday, checkered history. Faraday actually was a part-time chemist, right? Then he actually was interested in chemistry, although his job was not a chemistry background person. Our CNR Rao used to tell, Faraday kept on doing it. Then in between the two laws of electrolysis, he postulated. And whatever we are doing now in electrochemistry, 90% is due to Michael Faraday. Delta G equal to minus NFEV, right? That is due to Faraday. Then Faraday's laws of electrolysis due to him. Then how do you quantify the electrodeposited amount? That's also due to Faraday, right? Only thing is in Faraday's time, there was no Nobel Prize. So otherwise you would have got many Nobel Prizes. So when we proceed, we will get answer to the question that you asked in between. We'll get the answer. Anything not clear? Okay, what we'll do, we finish 10 minutes ahead of what I wanted to do in the morning. So I would complete it in 10 minutes. Then I will go to second part. Second part will be more appealing mainly because it will have more chemistry compared to concept that is coming now. Now we are having more concepts. In the second part, which will come after 10 minutes, you will have more applications to appreciate the electrochemistry. Now you can see here, in chemical kinetics, we ask the question, what is the order of the reaction, what is molecularity and so on. In electrode kinetics, what is electrode kinetics? Kinetics of electrode reactions, kinetics of electrochemical processes. That is electrode kinetics. There we ask the question, what is the current when you apply a potential? Sir, what is the equivalent of the rate constant in electrochemistry? Exchange current density. The exchange current density is equivalent to rate constant in chemical kinetics. Sir, what is meant by exchange? Electrons are exchanged between solution and the metal. So electrons are exchanged, so exchange. Current, we know we are measuring current. Why density is coming? Because we want to normalize with respect to area of the electrode. One person may use a big electrode, another can use a small electrode. So we want to normalize. To normalize what we do, current per unit area. So current density comes. Exchange comes because electrons are exchanged between metal and the solution. So exchange current density. It is directly proportional to rate constant. In electrochemistry, when you say a reaction is very fast, what you mean is exchange current density is very large. Sir, what is a very large number? 100 ampere per centimeter square. It's a very large number. Normally, it will order of microampere per cm squared, ampere and so on. If a 100 ampere per centimeter square, it's a very, very fast reaction. Just like you say rate constant large means reaction is fast, here exchange current density large means reaction is very fast. Right? That's very important. Then morning I said in the Arrhenius equation, when you write K equal to A power minus EA by RT, when you take L and K, it will be linearly proportional to activation energy. Then Marcus comes along and says, no, it can be a quadratic dependence on activation energy. That means L and K is E squared. Then he proved it by experiment. That took a long time. So he got the theory in 1962. Nobel Prize came in 92. Because the experiment that he wanted was carried out much, much later. So Marcus got Nobel Prize because it was a breakthrough compared to Arrhenius equation kinetics. The big difference. There it was linear, Marcus says quadratic. and experimentally they proved it. So he got Nobel Prize in 1990. I also met Marcus 15 years back at the conference. Then in all electrochemical reactions, either it is oxidation or reduction. Right? All processes are either oxidation or reduction. Right? So whenever you have potential measurement, you cannot measure your potential without a reference electrode. So people thought of the postulating reference electrode. Oldest reference electrode was platinum, standard hydrogen electrode. Why they took platinum? Because it gave reproducible results. Today we have silver electrode, calcium electrode, many electrodes, organic electrode, non-aqueous electrode, and so on. Right? Ferrocene, ferrocenium, and so on. So compared to olden days when we had standard hydrogen electrode, today we have many reference electrodes. It depends on what system you are studying. Accordingly, you can choose the reference electrode. We can buy in the market easily. We can also prepare in our lab many of the reference electrodes. Then Butler-Murray equation morning I told you. What was that? It is a relation between current and potential. It is non-linear Ohm's law. Ohm's law says V equal to IR. Voltage equal to current into resistance. Voltage is directly proportional to current in Ohm's law. In Butler-Murray equation, it's non-linear relation. That means current is exponentially related to potential. That is the Butler-Murray equation. See the difference. Electrochemistry, we are having non-linear Ohm's law, which is known by the name Butler-Murray equation. 1930 he postulated. It has two parameters. What are they? One is exchange current density I0, another is alpha. I0 I just now told it is nothing but a rate constant. Alpha is nothing but similar to activation energy. So if somebody reports I0 and alpha, they know completely everything about the electrochemical reaction. Just like you know pre-exponential factor and activation energy in kinetics, here if you know I0 and alpha, you know completely everything about the electrochemical reaction. Even today, there is no equation apart from Butler-Murray equation. Nobody has gone beyond it. We had done in some of our lab. I will do it in the second part. What we did away from much superior than Butler-Murray equation. Now, what is the limitation? Limitation is the way Butler-Murray equation are derived. You will see it was done using thermodynamic arguments. They had a free energy diagram and then they had the energy barrier. They wrote the Gibbs energy changes for the anode process and cathodic process. But you ask the question, sir, I want to know where is the metal in your Butler-Murray equation? It is not there. Where are ions present explicitly? It is not there. Where is solvent present? It is not there. That means Butler-Murray equation for chemists have no use. If you want to look into chemistry behind the reaction, Butler-Murray equation is simply not possible. It simply cannot do it because it has no parameter for every metal. Suppose I take platinum, silver, gold, then I0 will be different for a reaction, but there is no parameter in the equation for this. Similarly, I take, let us say, ferrous ion, then cadmium ion, ferric ion. There is no parameter for the reactant in the Butler-Murray equation. Then how does Butler-Murray equation escape with this? Because you can get I0 and alpha from the graph and interpret somewhat qualitatively. So you are escaping big questions from Butler-Murray equation. That's what I told here. We have one additional parameter, exchange current density and the symmetry factor or transfer coefficient. What is symmetry factor? It tells the symmetry between the active energy barrier. That's all. Normally it value is 0.5. We say it is symmetrically situated, so symmetry factor is 0.5. It is always a fraction less than 1, so it is 0.5 in general. So using I0 and alpha, we get complete information qualitatively in any electrochemical reaction. Now, like I told, whenever electrochemical system, you have many parameters. What are the processes? It can be adsorption of ions or molecules. Some ions from the solution can come to electrode surface and get absorbed. They can be physisorption or chemisorption. Suppose I want to study some organic compound adsorption, I can do it. I'll simply put the organic compound in the solution, apply electric field, the organic compound will come to electrode surface and get absorbed. In fact, this is the method by which they do corrosion inhibition. Right? To prevent corrosion, what they will do? They will add some inhibitor which will get absorbed on the surface and prevent the corrosion of, let us say, stainless steel or iron or something. So, absorption of ions or molecules is very important in corrosion and electrode deposition and so on. Then you have a lot of theories. Statistical mechanics is there in the morning, I said. Then you have quantum mechanics, Schrodinger equation and so on. Then you have computer simulation. You can do Monte Carlo simulation, what they call, or molecular dynamics. We have very good software packages in our institute. So anyone can work on that and get some information on that. Then you have experiments, titrations, amperometric titrations, conductometric titration, potentiometric titration, so on. Then we have voltammetry, cyclic voltammetry, very popular technique. What we do there, we apply a potential as a function of scan rate, measure current at various scan rates. Our MSc lab, even today we have MSc lab, there the students do experiments, cyclic voltammetry, 3 experiments on 3 different weeks. Right? If you have time, our KMS will take you to our MSc lab, you can see. We have Thursday and Friday full MSc lab. Right? They will do electrochemistry experiment about 50% of the time. So you have many experiment on cyclic voltammetry. Then impedance technique. When you have alternating frequency, alternating potential, you have impedance technique. Then coulometry. How much coulombs you passed in a reaction, that is called coulometry. Amperometry means how much current, so amperometry. How much potential, potentiometry. How much impedance, impedimetry. So like that it keeps on going. Then you have many important things like fuel cells, batteries, supercapacitors and so on. Right? We'll be seeing it in the second part. Today, if you say chemical reviews, lot of articles you will see on electrochemical science and technology in various aspects. Today, a lot of papers are coming in all journals, various reviews. So I quoted a little bit from yesterday I was seeing. Then you ask the question, sorry, electrode. What type of electrode do you employ? Electrode can be metal, platinum, silver, gold, nickel, and so on. It can also be alloys, or it can be semiconductor. You can also have chemically modified electrodes. What is that? You can modify the electrode with respect to using another metal. That means what? You deposit one metal on another metal, that also you can use. You can coat a polymer film on a metal, it can be a polymer film covered electrode. Right? So various electrodes you can prepare. Metals, alloys, semiconductors, modified electrodes. So we'll be seeing that in second part. Then electrode can be macro size electrode, a chemical reactor, for example. It can be micro electrode. Micro means what? Micron thickness, 10 power minus 6 meter thickness. Micro. Ultra micro means lower than micron. So you have ultra micro. All are available in the market. Today we can buy that. Simply place an order, it will come within no time. So our students used to buy from the catalog and immediately start the experiment. Available ultra micro, gold, silver, nickel, palladium, many metals are available today. Then geometry. Geometry means when you have disk geometry is there, band geometry is there, cylindrical geometry, electrodes. Sir, why we have so many geometry? Because current distribution will be dictated by the geometry. That's why normally people go to disk or sphere or band, but many geometries are available depending upon what they are looking for. So accordingly you can have many other geometry. Then morphology, which also we'll see second part. Nano wire, nano rod, all are available. Today we have gold nano rod experiments, then experiments on silver dendrites and so on. Sir, why we have so much of diversity? It is because availability, cost. We can't have very costly electrode, platinum every time, or rhodium every time, ruthenium every time. So we need inexpensive electrode. What is the most inexpensive electrode? Stainless steel. Most of the experiment in our lab, I did stainless steel electrode. Go to Velachery and buy and come. Very simple. Or pencil graphite. The electrode that is present in your pencil. You can remove the graphite and use it as electrode. Then fabrication. You should be able to fabricate it. Then only it will come to market. So availability very important. Then scale up. You need to scale up. Because industry wants at a very large scale. They don't want your milligram amount of compound. They want in tons and kilograms. So scale up is important. All electrical experiments have only one thing. Either you apply potential and measure current, or you apply current and measure potential. No other thing is there. Occasionally you will have time also as a variable. That means in a steady state experiment, time will be 10 to infinity. That means there will be no time dependence of the process. Then it is called steady state experiment. When you write your current equation, there will be no time coming in the equation. It is called steady state experiment. Suppose your current has a function of time, it will be a time dependent experiment or transient experiment. In chronoamperometry, you measure current as a function of time. Chrono means chronology. So current, if you measure function of time, it becomes chronoamperometry. Suppose you measure potential as a function of time, it is chronopotential. Chrono means time dependence, essentially. So you have time, current, potential, concentration, that's all. If you are looking at current and concentration, it becomes a titration type experiment. Amperometric titration. If you have potential versus concentration, it is potentiometric experiment. If you have current versus time, it is essentially chronoamperometric. So all electrical experiments are relation between. Amazing, right? Nothing else is there except this. Then, like I said, steady state and transient. Steady state means time will tend to infinity. That means you will wait till the system comes to steady state. Otherwise, it is transient, current as function of time. What do you look for in this? You look for in the yield reaction mechanism. That's what you are looking for. You are looking for mechanism of the reaction. If you are doing organic reactions, you would like to see the synthesis, whether you got the product you wanted, whether you got sufficient yield, whether you got specifically that product. Right? All this you will ask. Right? Then we'll come to theoretical assembly in the second part. Now, morning some questions were asked about the reaction. So we'll take a typical, very important reaction, which is called hydrogen evolution reaction. Typically, it is written as H3O plus electron giving half H2. Sir, why you took this reaction? It is industrially very, very important. Apart from that, you have rate constant available on nearly 50 different metals. So, the correct theory should explain all the 50 dependence on metals. That means when somebody gives exchange condensity on 50 different metals, the theory should explain the data on all the 50 metals. That's what we did long back. So what we did, we put the work function of the metals. We also put the reactant size and charges. We also put absorption isotherm. Finally, we got the exchange condensity of hydrogen evolution reaction. I'm not showing the data because I don't have the time to show that here. But what is important, it has been done by us somewhere in year 2000. We had published nearly 20 papers on this, various aspects on this. So what is the message in this? The message is, even the Butler-Murray equation has limitations. You can take any new reaction and try to work out a theory and reproduce the experimental data. It will be an entirely path-breaking discovery. No one has done that. Right? So that is something I would like to tell here. So this is what I left in the morning. Essentially, I have told how electrochemical systems are very important. and what information you get, how it is more and more challenging these days to make contributions in electrochemical systems. So in this first part, any question you can ask, then we'll go to second part. Feel free to ask, don't hesitate. Plenty of time. Any question? Any question till now? Yes.
Reaction. The answer potential is the potential with the reactant start. What is over potential means, sir?
Over potential is defined as potential over and above the equilibrium potential. That is called over potential. Whenever you have over potential 0, that means net current is 0. That means I equal to I naught, all this is coming, At the over potential, when over potential is 0, anodic current equal to cathodic current. IA, which is anodic current, equal to IC, which is cathodic current, equal to I naught. That is over potential. Answer potential at which a reaction starts occurring. Right? Both are equally important. Right? What's our aim? Our aim in any experiment is to minimize the over potential. When you want to minimize the over potential, what will happen? There will be no net reaction. Because forward rate equal to backward rate. So no net reaction will be there. We want to minimize the over potential. At the same time, we want the reaction to occur. There are many types of over potential. What are they? Activation over potential, ohmic over potential, concentration over potential, and so on. Each of them is due to a different cause. Ohmic over potential means it is due to resistance of the solution. Activation over potential it is due to the activation energy barrier. Diffusion over potential means it is due to diffusion limitation of the reactant. All together is total over potential that we get in the reaction, in the experiment. Any other questions? Any other question? Otherwise, we'll go to the second one, which is that this will be a little more applied compared to the first part. Here, what I decided to discuss was the following. I decided to discuss more nanostructured materials because this is what the fashion today, nanostructures, and so on. So, I will spend some time on nanostructured materials and electrode modification, right? So, I would, morning we have been discussing only metal electrolyte interface. There are other interfaces, namely liquid-liquid interface. That means you can have water acetonitrate, water dimethyl formamide, water dichloromethane, and so on. That means you can have one electrolyte in aqueous phase, another electrolyte in organic phase. That is called interface between two immiscible electrolyte solutions. ITIES, interface between two immiscible electrolyte solutions. Right? Now, I had a two DST project long back. It's a very important field. So, DST gave two projects to me on liquid interfaces. So, we'll spend some time on that. Then we'll also spend some time on potential distribution. Like you said, over potential, what are the components of our potential, and so on. Then we have dynamics, time dependence of processing. That also we'll see sometime. Then analytical chemistry, that means you can have qualitative analysis, quantitative analysis, and so on. Then electrocatalysis, all reactions are catalyzed by electrodes. Right? Energy storage, primary battery, and so on. Then corrosion prevention. Then I will discuss about the modification of electrodes using redox polymer and then conducting polymer, and then a new concept called under potential deposition. This is what we have been seeing from the morning. In ionics, you have differential theory and beyond. Today, we have many advanced theories beyond differential theory. Right? We will not get time to discuss that. Then electrode kinetics. We have Butler equation, Special case of that is Staffel equation. Then Rudy Marcus Nobel laureate, Marcus theory also is there. Again for electrochemical reactions. Then electroorganic reaction, which is the, you can have synthesis of new compounds, mechanism of various electroorganic processes. Then you have bioelectrochemistry, ion transport in membranes and biosensors, sensing analytes using glucose, urea, dopamine, using various methods. Then energy storage devices. Then we have steady state and transient experiments. Like I said, steady state means time tends to infinity, no time dependence. Transient means current or potential will be a function of time. It is called transient electrochemical technique. Then impedancy when you apply the frequency also. Today morning there's a question on the convection, which is the rotating disc electrode. Normally we keep the electrode stationary in the table. You can also rotate the electrode, which is called rotating disc electrode. There what you do, you deliberately rotate the electrode with a rotation speed so that reactant can come to electrode surface faster. You can control the arrival of the reactant to electrode surface by proper rotation of the electrode. That technique is called rotating disc electrode. For example, an ion can move only at a particular speed towards the electrode surface. For my purpose, it is very, very slow. I don't want that. Then what I do, I rotate the electrode so that reactant can come quickly to the electrode. That's a convection. These electrochemists have thought of all these things. They want to accelerate the reaction, but the ion has their own limitation. They cannot travel faster than this, governed by diffusion coefficient. So they do convection by rotating the electrode. It's available now in market. One can buy the RDE setup. It is available platinum, nickel, and things. Right? So the electrode can be of any metal, but there is a rotating arrangement there. Then you can do current potential measurement on this also. Right? So you have diffusion, migration, and convection. Convection is a rotating disc electrode. Migration is what you do in conductometry. We apply potential, measure current, for example. Okay. Then you have various things like amperometry, voltammetry, polarography. Polarography is nothing but voltammetry, except electrode is dropping mercury electrode. That's the only difference. Then amperometry, you measure current as a function of time. Corrosion, like I said, adsorption isotherms. How to reduce adsorption of various organic compounds. So that is called adsorption isotherm. We cannot use Langmuir, Frumkin, all these things. We cannot use Langmuir isotherm or BET here because they don't have potential dependence of surface coverage. So isotherm we study in adsorption of gases and solids are not useful to me in electrochemistry. You see that? So we need to do everything once again. We cannot go back to old physical chemistry that we studied. And electrodes can be macro, micro, and ultra micro. Macro size is macro size electrode, very large. Micro is about micron dimension. Ultra micro means lower than micron. Ultra micro electrode. They have very interesting property in terms of double layer corrections, rate constant, how to accurately get. All of them are possible by ultra micro electrode. That's why they devised all this. Normally, when you do measurement, you don't know how to correct for electrical double layer effects. Like today morning, someone asked. Whereas, if you use ultra micro electrode, the rate constant you get is exact number without interference from double layer. Why does it come? I can explain that at the end. Then I had written an article recently on the what makes electrochemistry interesting. Today I have discussed in this invited article sometime back. Are there other interfaces apart from metal electrode interface, which is electrode electrode interface? Now we have interface between two liquids. Interface between two immiscible electrolyte solutions. ITIES, right? Abbreviated like that. Then Michael Feld himself has prepared colloidal metal water diethyl interface, all this. Right? So today an emerging field in electrochemistry is the phenomena occurring between liquid interfaces. Why it is very interesting, I will show you in the next slide. You see here, when you have two different liquids, there can be what is called as a sharp boundary. What is meant by sharp boundary? A reactant that is present here cannot come here. Suppose this is water, let us say. This, let us say, some organic solvent, dichloromethane, dimethyl formamide, some such thing. Then this is diffuse boundary. What is that? You can see here water molecule present here also. You can see organic phase molecule present here also. That means what? A reactant that is present here can undergo reaction within here, and within here. Whereas in a sharp boundary, a reactant present here can only react with a reactant here. Sharp boundary. Boundary is so sharp that a reaction will occur only when the reactant is present here, with the reactant present here. Whereas here you can see a reactant can occur, the reaction occur between here and here, between here and here, and between here. That is called diffuse boundary. We can do very interesting electrochemistry on these type of systems. Now you will see why they have become very popular, this field. You can prepare nanostructured materials using liquid interfaces. Right? You see here, we can have metals like copper, silver, gold, platinum, palladium prepared using various LL interfaces, liquid/liquid interfaces. You can also have bimetallic, silver, copper, nickel, tin, nickel, copper, and so on. You can also have conducting polymers prepared using liquid interfaces. All this we have done in our lab those days. So actually we did all this in our lab the past 15 years or so. Right? Very simple experiment anyone can do with very minimal equipment. Now, there is no general procedure in the sense that you need a lot of skill to get the compound. Simply by mixing the two reaction, mix the two solvent, product will not come. There is a lot of trial and error to go on. So a lot of skill is involved, lot of art is involved. Right? Repeated trials only will finally give the desired product. Right? But one more thing is we need extensive characterization like HR temp measurement, SCM measurement, XPS, and whatever it is. So many characterization facilities we need. Normally we have synthesis using chemical methods. You can also electrochemical methods like electrode deposition. Suppose I want gold nanostructure. What I will do? I will take a gold compound and see that it undergoes reduction and it gives nanomaterials on my stainless steel substrate. Right? So I can always have nanostructured materials coated on the electrode surface. That I can use as electrocatalyst. Very amazing. I needed to separately take the nanostructure. I can take the nanostructured covered electrode itself as electrocatalyst. So that's a very amazing thing. Then you have what is structure directing agent because you want a particular geometry like nano rod, nano wire, nanosphere. You have to choose appropriate structure directing agent. Then only it will come. Otherwise it will be agglomerated, there will be no structure there. Right? So that is one. Then you can have variety of choices here for binary solvents. You can have water chloroform, water dimethyl formamide, water acetone nitrile, and so on. Right? And we have done a lot of work on this. Now, this is a very interesting thing for you students. How a simple procedure by the Richard Kanner became a breakthrough. What he did was, he took aniline monomer and put ammonium persulfate in a water chloroform system. At the end of 10 minutes, he gets conducting polyaniline nanomaterial, nanostructures. Very simple experiment. No heating also involved. Aniline monomer and then two interfaces. That's all. How the simple technique gave polyaniline within 10 minutes. And remember, this is a very classic paper, cited more than 1,235 times. I mean, 1,235 times they have cited this paper. Very simple procedure. Any person can do such experiments. Take a monomer, take a binary liquid like water chloroform or some such thing, and then prepare it. Right. So next, if we go, in our own lab, we did the same procedure for metal polymer composite, silver polyindole, as a typical case. So again, we have taken dichloromethane here, water, dichloromethane, and then silver ion. Then we are getting beautiful geometry of silver polyindole composite. Two types we got. One is at the interface, another is at the organic phase. Then we'll go to next. You can see here how we are able to get at the end of 4 days, we are able to get the silver polyindole composite. Silver oxide, nitric acid. We also did polyindole, indole, ammonium persulfate, then we got polyindole conducting structure. Here also silver polyindole composite. This is the power of electrochemistry. On one side, we are exciting theory. On the other side, we are exciting experiments. This is what electrochemistry is fascinating for people. Then you see here, why we modify the electrode? Because noble metals are very expensive. Only if an inexpensive electrode, it can go to market. One of them is stainless steel, pencil graphite, and nickel foam, for example. Many other things are there which are available inexpensive. Right? Then hierarchy got because of the dropping mercury electrodes, a big breakthrough. Now challenge is what? You have to find a new electroanalytical technique with inexpensive surface. Unsolved question. How do you get a new electroanalytical technique with inexpensive electrodes? Then you see here, why should we modify the electrode? Because affordability. Gold as such is not affordable, so we modify the electrode. So affordability. Specificity. Unless we have specific purpose, then the electrode won't be useful, so we have to specificity. It should be a specific function. So function. You have different methods of deposition. What are they? Normal deposition that you do here. Another is what is called under potential deposition. Potential before the Nernst equation. That is called under potential deposition. That means there is another deposition that occurs before the Nernst E0 is occurring. That phenomenon is called under potential deposition. Plenty of work is going on in this. Then you have redox polymer electrode. Polymer in which you immobilize redox center is called redox polymer electrode. That means what? You take an electrode film, you take a polymer, in that polymer you put redox centers, that is called redox polymer electrode. Similarly, under potential deposition, which is also, I will spend some time on this. Then you have conducting polymer, which can be used as biosensor or supercapacitors. This is what I said, that's a redox polymer electrode. Suppose you have taken one electrode here, platinum or nickel or stainless steel, something, then you got a redox center, osmium bipedal complex in a polymer film. This entire thing is called redox polymer film. Sir, why are we doing this? Suppose your reaction is very slow at the electrode surface. Then this reaction is very fast. Then the electron comes here, comes here, comes here, comes here, up to this. Then your reactant will undergo reaction with the electrons here. So it is possible to make a reaction occur at the film solution interface because it was very slow at the electrode film interface. That's interesting. Then we had done a lot of work on synthesizing nanostructured bismuth, cobalt, palladium, silver, and so on. Then we also prepared polyaniline, polypyrrole, polythiophene, polyindole, and so on. Here you can see we have prepared gold nanoparticle of 5 nanometer size using what is called that surfactant cetyl trimethyl ammonium bromide. You can see here gold nano popcorn, gold nano tetrapod, nano bipod, all these you can see here. Excellent gold nanoparticle prepared effortlessly by a group in Calcutta, which is from the Dulal Senapati. He was my MSc student at that time, Debranjan Mandal. Then he finished. So you see how simple electrochemical methods are giving you gold nanostructures of various geometry. Now, what is interesting is this geometry has a profound effect in electrocatalysis. That means whether your geometry is popcorn or tetrapod, reaction rate is different. You can see here. Geometry is dictating electrocatalytic efficiency. First time it was shown here, where electrode geometry seems to influence the rate constants. Right? That is very important. Then here you can see we have prepared cobalt microstructures using the same potential deposition at various concentrations of boric acid. It acts as a structure directing agent, 20 millimolar, 0.1 molar, all these various geometries are coming for cobalt. Then we have many other things. Silver polygons. This also we prepared on indium tin oxide. Using chronoamperometry, you can see working electrode, counter, reference electrode, and so on. And then you'll see very good geometry. You see here, various geometries are coming for silver polygons. Sir, why you are showing this? It is because to show simply by applying the potential with silver nitrate solution on a working electrode, you get all the geometry. There is no other technique better than this to get nanostructure because there is no high temperature, there is no exotic solution. Simply apply a potential, take a silver nitrate solution and take one electrode, that's all. Nothing else. That is the polar electrochemistry where you can synthesize exotic materials by simple techniques. You don't do a large number of reaction steps, 15 steps, 20 steps like you do in other fields. So here, all you need is a beaker, 3 electrode setup, power supply, that's all. Nothing else. That's the power of the electrochemical experiments. Then here we prepared polypyrrole conducting polymer using again same electrode deposition technique. This we used for supercapacitor purpose actually. No time for supercapacitor today, it's a big field, but you can see we have taken pencil graphite electrode, we synthesize polypyrrole microtubes. All these are microtubes. Various electrolytes, HCl, nitric acid, sulfuric acid, all these things. Again, very simple electrode deposition technique, nothing, no exotic. Then we used it for studying as a supercapacitor material. Then I spent 1 minute on this, what is called under potential deposition. What is that? If we have deposition at potential positive to enhanced potential, it is called under potential deposition. Because normally we don't expect it. Only when you go away from enhanced potential, reaction should occur. Whereas some deposition systems occur where it is occurring before the enhanced potential. Right? Very interesting things are here. For electrocatalysis, we can apply UPD systems, or we can also use it as supercapacitor, the systems, and so on. So this is what is the experiment. You can see this is called as the under potential shift. Thallium on silver. right? Normally, this peak would not have occurred, right? In the bulk deposition. Here it is under potential deposition. So this is called as the shift in the under potential deposition. Very long back, 1975, they did this. The theory is still not yet ready for. Then we have done it. You can see here. Right? This is the due to UPD phenomenon. This is due to bulk deposition. Large number of cycles we have done. That's why you see so many current. So 100 cycles, for example. Right? We have employed it to develop supercapacitor system. UPD thallium, onsil. We had a DRDO project some years back. Then we used that money for developing the supercapacitor system. You can also use it for sensing, let us say, nanomolar amount of various compounds. Here you can see what we have done is we coated silver nanoparticles on glassy carbon. Then we studied lead under potential deposition, which is here. Whereas if I don't have silver nanoparticle, I study lead on GC, glassy carbon, there is no peak here. Only when I coat silver nanoparticles on GC and study lead deposition, this peak is coming. And this I can use it to sense lead ions because it's a reversible process. I can do stripping of the lead ion in the solution. I can exactly get the amount that is present in unknown solution of lead ions. Right? In a biosensor, what are you looking for? You are looking for linearity, linear range. Then it should be very sensitive. You should be selective. That means you should have no interference. It should be quickly responding. So response time. Then it should be very stable because we should be keeping the shelf. Again and again we should use it. Then robustness. You should keep on using it. It should be affordable. Then you have many techniques: conductometry, voltammetry, amperometry, potentiometry. Then what you do? You draw calibration curve and do to predict the unknown concentration. Then we have done a lot of work on glucose sensing, catechol, urea, PAM selectivity, and so on, using various conducting polymers. One example I take, which is sensing of urea. What we have done, we have taken a pyrrole monomer, polymerized on platinum, and used this polypyrrole coated electrode to sense urea. Then you can see the way it is sensed here. This is the typical chronoamperogram, current versus time. What is this step indicate? This indicates the amount that you added, amount of the solution you added. So you draw a calibration. If somebody gives unknown solution of urea, I will measure the current and come to this calibration curve and predict the amount. Right? Very simple. All I have to do is, if they give unknown sample, I will measure the current and then see it here and predict the concentration. That's the principle in the biosensor. Same thing you can also do using what is known as the impedance data. This is called as the Nyquist plot. Imaginary part of the impedance versus the real part of the impedance. Then this is the one I said today morning: HN current density, number of electrons, Faraday, gas constant, absolute temperature. This I naught is HN current density. A is area of the electrode. C naught is concentration. K naught is standard rate constant. So finally, we'll come to the summary of second part, which we did in the afternoon. We said how to do under potential deposition, what is the importance of that. Then how to prepare nanostructured materials, I have highlighted. Then conducting polymer, how to synthesize, I explained briefly. Then the interface between two emitters also I pointed out. Then in this article I said that exciting times are ahead for electrochemistry education and research now. With this I will conclude and I thank you for listening. Any questions, feel free to ask. Don't hesitate. No, that's correct question. It depends upon the convention. For example, there are two types of convention. One is American convention, another is European convention. You can always interchange the axis. It is enough if we know the process rather than the direction of the current or the sign of the current. Because American instrument, you have a different convention for cathodic and anodic current. In the European convention, it's different convention. That's only it is. So it only depends. Yes, sir. Now here, that's why you can see here, deposition, where it is occurring, you can see here. Here you can see, right? This is the bulk deposition. Then you pick, right? Then the reverse, right? So, whichever way you use the convention, the shape will be almost same. So, it will not make a difference. Any other question? Yeah, because many times the polymer film covered electrode, when you keep potential cycling, the polymer film will disintegrate. So polymer film will not be stable beyond a point. Also, when you use repeatedly, the electrode will get poisoned. Suppose you have methanol fuel cell, there carbon monoxide poisoning can come. So either polymer film can disintegrate or the electrode can become slowly inactive. Because you keep repeated use, so it may be inactive. So it is no longer active to the extent you wanted. Yeah, that is true. That is true. Yeah, that's what we do. In fact, when we do experiment on glassy cover electrode, we do experiment some 10-15 times. Again, we do pre-cleaning and again we reactivate in a particular solution to make it more active, equally active as in the beginning. We do it. We can always activate the electrode by repeated polishing procedures.
Slide number you explained about liquid.
Yes.
So is there any
Yes, that's true. In fact, liquid interface itself is a correct case studies to study what is known as capillary width. So people are struggling to find the interfacial tension between two liquids. So capillary width, there is a theory for the capillary phenomena and LL interfaces. It is existing, but people have not explored much. I had one paper long back from Germany on this, where we use the interfaces to estimate capillary width of the interfaces. Yes, it is correct, but not much activity has taken place on it. It's a correct question, but capillary action is least understood as of now. Any other question from this side? From this side, nothing is coming. Any question? Reactant means, suppose we study ferricyanide ferrocyanide last couple. This reaction can be electron transfer, any oxidation process or reduction process. Then what we do, like we saw in that impedance diagram, it will tell clearly with this diagram. I will show that. So that will very clearly we can answer. I will show that along with the graph. It will be very clear now. Right. Now, here, whenever you are studying the, let us say, urea oxidation, let's say, the reactant here is urea. Then, when you compute this type of Nyquist plot, when you construct, you will have the one is called this intercept. This is called RCT, which is charge transfer resistance. And this number nearly 0 is called solution resistance. So one is RS, solution resistance, one is RCT, charge transfer, and this is related to I0. This I0 is related to rate constant of the urea reaction. So you are able to study rate constant using impedance technique. So here reactant is urea. Similarly, every case reactant will be some other thing, ferricyanide or cadmium nitrate, something. So this I naught is referring to the exchange condensity of the electron transfer reaction you are considering. Any other doubt? That's a good question. There is a phenomenon called cold fusion some time back, where they were able to get nuclear energy by simple electrolysis of deuterium salt. So that was controversial. Then that paper had to be withdrawn and done. So that isotope hydrogen still has not been found favorable. As or no, hydrogen gas only. It's called cold fusion, 1982 or somewhere they found it, and then the authors had to withdraw the paper because nobody could reproduce it. What they demonstrated was they found nuclear energy being produced in a test tube when they electrolyze the deuterium salt. Right? If you see the paper Fleischmann and Pons paper, they are demonstrated, but then nobody could reproduce the result. Then they were fired from the job after that, after they became addressless. Both are essentially similar in terms of interpretation. In the electrochemical series, you are reporting in terms of the standard electrophoton. In the galvanic series, you are reporting in terms of the efficiency of a galvanic replacement reaction. For example, when you want to develop a binary alloy, when you want to synthesize, we look into the galvanic series and see whether that metal can replace the other metal. So that is called galvanic replacement. In the electromotive series, electrochemical series, you are reporting in terms of the E0 activity like reduction to oxidation, zero, and so on. Any other question? Yes.
Hydrogen. So, what do you think? Maybe is there any alternatives or something like in a safer way to produce hydrogen for future purposes?
Yes. So what they are nowadays doing is they are producing hydrogen in situ so that it need not be taken out of the system. That means they will electrolyze water, get the hydrogen, again use it for a purpose so that hydrogen is not stored separately. Right? That is one approach they are doing, and the safety more or less they are now overcome. Right? Using many other type of compound. Right. So that is now safety is not the important thing here. More important is the expensiveness. For example, right now they have not found any affordable catalyst for the fuel cell. Whether it is hydrogen fuel cell or methanol fuel cell, catalysts are expensive. That is the reason why it is not still market is. It is not the storage or safety, it is more the expensive part. Still they are finding the normal vehicle cheaper than the electric vehicles because of the catalyst.
Catalyst for that reaction, maybe alloys could work. Right?
Alloys are they are trying.
Different compositions of alloys.
Alloys are they are trying. Alloys, oxides, many metal hydride batteries are there. They are not trying. The field is very, very active.
What are the different kinds of working electrode we use in cyclic cold?
It's up to you. Working electrode normally, if you can afford a glassy carbon is the best working electrode. Right? If you are having very good skill, even stainless steel is very good. Pencil graphite electrode is also very good. Nickel also will give as good a result as platinum. We found nickel gives the same result like platinum in cyclic photometry. So nickel very affordable we can buy. Then stainless steel, pencil graphite, and many other. Many of them one can use. It is no longer necessary to use platinum or palladium or gold. You can have pencil graphite electrode and maybe nickel, for example. Nickel foil we can buy in Velachery easily and use it. It gives same result, similar 90% of platinum.
What do you think about the screen printed carbon electrodes?
Uh-huh.
SPC.
Yeah. No, that is SPC. What's the question? SPC, the screen printed carbon electrode, there it comes as a 3 electrode arrangement once and for all. So it can be directly used in sensing analytes. Suppose you want to sense glucose or urea or dopamine, SPC if you buy and record either amperometry, chronoamperogram or voltommogram or any electrochemical technique, you can directly read the amount present from the SPCE data. Advanced SPCE is very inexpensive. You need not have to worry about 3 different electrode arranged here. Already it comes as a 3 electrode arrangement. Screen printed carbon electrode. One final question.
So in liquid deposition, does the polarity cause any difference in the polarity?
Yes, very much. Yes, very much. That is why that field is very active because we do not know what type of binary solvent we should employ. For example, water dichloroethane, will it be better than water dimethyl formamide? We don't know to begin with. But what we know is the dielectric constant of the both solutions play an important role. How much important we don't know. That's why the trial and error comes. Okay, we are behind time.